do two things today. We're going to actually cover an entire section which consists of 3 questions. And it's section 2.4, and it's called the precise definition of a limit. And we are going to do all 3 questions together. And the answers are pretty short and straightforward. They're basically the reason why the limit process works. And essentially what that does is, and I'm going to give you the theory behind it. Now, I don't want you to get too caught up on this and think this is a biggie. So let me tell you some things that will make you feel a little bit or a lot better. You won't get any online test questions on this. And you won't get any midterm exam question on this. And you won't get any finals on it. And the 3 homework questions, we are all going to do them together. So as long as you've got my answer, when you go on to do your own homework, you can just fill them in and you'll be done. I want to try and just focus then on what the heck they are trying to do in this section. What they are looking at is a kind of way to think of limits, and they do it in almost a very lawyer-esque way, right? So I want you to imagine that we have a function that has nothing wrong with it. And by that I mean it's a nice, smooth, well, maybe not so smooth, but it's a nice curve. And I am interested at this point here, x equals a. And at this point, x equals a, would you agree that the value of the function is f of a? That seem reasonable? Nothing special going on. So we would say that the overall limit of x tending to a of this function, f of x, is simply just the value of the function at a. It's a very, it's just a nice curve where nothing is happening, right? No vertical asymptotes, no funny holes or any weird stuff. It's the simplest case. What do we mean then by that the limit is x tends to a of this function is the same thing as the value? And it looks something like this. We can find a number delta greater than 0 such that the absolute value of x take away a less than delta, so such that for any x where this is true, the absolute value of f of x take away f of a will be less than epsilon, where epsilon is any number. Let's put it in any positive number. So it's like a lawyer got involved with mathematics, and that is basically the formal definition of what it means to say this. So how does that work? You give me any value of epsilon that you like, any positive number, and I can show you this, right? So let's suppose that you decide that epsilon is going to be that distance from there to there. Can you imagine that I could do either side of it, right? So what I've got is a little range of values, right? Now, if I go to here, and then I go to here, what you've got is a big chunk of values of x. And we can show that any value of x in that range, this is going to be true. Now, if you make epsilon really tight, right? So if I imagine, this picture's going to get ridiculously ugly in a minute, but can you imagine I made epsilon almost a dot worth? Can you see that if you come through here, you got to there, and you come through here, what's it? God, my drawing's bad. Right, you get to here to here. Anything in that range As long as you pick a value in that range, it's going to give you an answer inside that little range. There are much better videos because they can do animations and things that you might want to look if you feel that you want to get this. The way I look at it is, if you take a value and you say, I want to get the answer within that little range here, I can find a delta down here where all the x's inside that delta range, every single one of them will give you a value that's inside the range that you're interested in. So couldn't you make epsilon almost 0? But you'd still be able to get an interval where everybody would fit inside that very narrow window. That's kind of my way of thinking about that. So now we're going to show you the 3 questions that kind of apply that. So go hunting for a good video on that. I think I put some in Canvas where you can maybe visualize it if that helps you. So here is the first question. We are being asked to find the delta, right? Because that's typically, so that the value of the function, square root of x, take away 2, is inside that range. Now, if you look over here, can you see that they've said there's 2, the answer, 0.4 above, 0.4 below. So they're saying epsilon is equal to 0.4, which is what's going on there. So how do we find the delta? Well, if you take this green line at 2.4, it hits the graph here. We need to find that number. And then it goes along and it hits the graph here, and we need to find that number. The delta that you're going to write down, and that's the answer that goes here, is the distance between the middle, which is 4, and the outsides. And that number might be 0.1, 0.06. That's the guy we're after. So I'm now going to return to my whiteboard so I can draw like pictures of what's happening. So this is my attempt at drawing the picture that was there. There is the square root of x function. Somewhere around about here we have 2. Change of color might help. Up here we've got 2.4. And that's going to take me to here. And there's a little question mark there. Down here is going to be, what, 1.6. That's going to get me here. And there's a little question mark here. And right in the middle, we've got the answer 2 and 4. And we are trying to find that distance there. Now, if this number here is 2.4, shouldn't we be able to find x? So how would I do that? Well, y equals the square root of x. The y value is 2.4. So 2.4 is the square root of x. Okay, what can I do to both sides to find x?
Square them?
Yeah, so 2.4 squared. So x is going to be 2.4 squared, which I get to be 5.76. So that means I know this guy. This guy here is 5.76. Now, let's find the other one, just for completeness sake. So we have the y equals square root of x, only this time isn't the number 1.6. And if we square both sides, we'll get x. And if I go 1.6 and I square it, I will get 2.56, which means I now know that number. So all we need to figure out now is what's delta. Now, isn't the delta the distance between here and here? Now, I can probably do that in my head. I hope I can anyway. 5.76 take away 4, I get 1.76. Are we good? Now, if you go 2.564, would you agree if you subtract them, you get 1.44? Do you notice it's not symmetric? You know, one side's the distance is a bit bigger than the other, right? Yet the answer that we're meant to write in is just a single number. Which of the two should you always pick if one side is a little bit bigger or smaller than the other? What do you think the rule is for which one you pick to make sure everybody in this range fits within that narrow band? The big or the smaller? What do you think?
I guess the bigger, but that's just a guess.
That's a guess. Okay. Well, guesses are good because it means you're trying to take part. So I'm going to tell you, no, it's not that one. So that means you know the answer because it's now the small one. So when you do these questions, you'll find the big answer, right? And you find the small delta, and you always choose the smaller one of the two. And that's to be safe, right? If you pick the smaller one, won't you guarantee everybody's going to work? If you pick the bigger one, there might be some values that are outside the range, right? When you go up and along, they're not quite going to fit. And that's the answer to the first question, 1.46.
1.46?
Yeah.
Is it not 1.44?
And did I go and screw up? I did. It's 1 point. What is it anyway? 1 point. Oh, darn it. Sorry, 1.44. Yes, I did. I screwed up. Thankfully, it's still the right answer. Now, 1.44. Right, here's your second one. In this question, they don't even tell you what the function is. But right in the middle, they give you 1. And on this side here, they tell you it's 1.1. And on this side here, it tells you it's 0.7. So if we go this way, this time I'll try and subtract correctly, it's 0.1. And if you go this way, isn't it 0.3? So what is the missing delta? Point 1 or 0.3? Which one do you choose when you've got a choice?
0.1.
Okay, that one was easy. Agreed? That's 2 questions done. This is going to be a world record for the quickest homework ever. Right, here is our final one. It's going to be y equals x squared. This guy is 1. This guy is 0.5. Gives you a question mark. This guy is 1. Gives you 1. On this side, it's 1.5. And on this side, you get a question mark. And just like every other question, we're going hunting for delta. Okay, let's get this one here where my finger is pointing. We know that y equals x squared, and we know the y coordinate is 1.5. Oh, and they want delta to 3 decimal places. Okay. What will I do to both sides this time to get x?
Square that or square root them.
Okay. And that's not going to be anywhere near as pretty as the other one. So that's the answer to 3 decimal places. So the one that goes here is 1.225. And then on the other side, it's 0.5. And if you take the square root of 0.5, we'll get 0.707. So let's see what the deltas are. From the middle to here is nothing 0.225, and from the middle to here, it's 0.293. And the smaller one then is 0.225. So they don't expect you to do much with these. It's really just, if I was dragged into a court of law and they said, look, you're telling people you can get these things called left limits and right limits, and what's your justification behind it? And I could say, well, this is the formal definition of a limit. This is how we could do it numerically. And now we can now look at the result and basic generalize it. And you know, all the techniques that we know, like factor and cancel and all those clever stuff like that, we can prove them using this technique. would you agree you wouldn't want to do any limit question doing it this way, right? That would take you forever in a day. But theoretically, if we had to, we could. So it isn't a good mathematical foundation. And that's the end of that section. You've got all 3 homework questions done. If you missed an answer, you can look at the video again. And now we're on to our next section.
I have just a quick question.
Sure.
Do you ever run into problems where the top one and the bottom one cross each other? For example, the 0.5 would maybe extend way out.
It could, I guess, yeah. And that would mean that your delta would be the other side, the shorter distance.
Okay, but it would
So-
still include the center point because it
Yeah,
maybe
you always have a
crosses
center
there.
point, and one of them will be this side of the center, and the other will always be to the left. So you won't have 2 points to the left of the center. There's always one to the right of the center point, and the other one will always be to the left. That you can't not have that happen. That's going to
Okay.
guarantee.
Okay,
So here's our new guy. And this one is not going to take 10 minutes. This one's going to take today and tomorrow, and who knows how long. But it's going to take a fair chunk of time. And we are going to do a bit of theory before we go anywhere near calculations. There's a concept in mathematics called continuity, which is basically what we mean in mathematics when we say a curve is nice. So let me show you a nice function. I'm going to start at A and just finish at B. And so it starts here and it kind of goes there and it finishes there. This function that I've just drawn, right, from there to there, this function, we call it continuous. So a continuous function has limits for all its values. And in particular, won't the limit at any value you like C? It will exist, and it will just be the value of the function C. So when you look at a function and you want to say, what does a continuous function look like? Here's my visual thing. Imagine that this is a road, and you're a little fly and you're traveling on a little fly car. Can you travel from the beginning to the end without being killed? And if you say yes, the function is continuous. So would you agree that is just a nice smooth curve? That's what continuous looks like. So we are going to look at all the things that are not continuous. So parts of a graph, and it's typically parts of the graph, right? One place that has a problem, right? And we're going to look at when it's not continuous. And that is sometimes also called the word discontinuous. So not continuous or discontinuous, it's the same thing, right? Let's look at some examples of what that might look like. I'll put numbers in. There's one, and it curves, and it finishes here. And that's 5. And this guy here is at 3. Now, the problem with this curve is, do you see there's a little hole? If you were that little fly traveling along the curve, wouldn't you fall into that hole and get killed? That is discontinuous, right? So this function, so f of x is, I'll use not continuous, is not continuous at x equals 3. And you might say, why not? Would you agree that the left limit and the right limit exist? Let's pretend that number there is 7. Isn't the problem there's a hole? That makes it not continuous. So it's not continuous. If I went and said to you, what's the limit as x tends to 3 of f of x, you would say that the answer was whatever, 7. You notice that exists, but that's not equal to the value of the function at 3 because the value of the function of 3 doesn't even exist. What about this function if I made one extra little thing? Suppose I gave it a dot away up here at 10. Would that help this function be continuous? No, wouldn't the little fly still get killed? So this type of discontinuity has a name. So if you want to tell someone what that kind of discontinuity is, it's called a removable discontinuity. Are we good? Nothing wrong with it, continuous everywhere. Hasn't this got a removable discontinuity? I guess if I'm doing its full title, at x equals 3, right? You tell people where the problem is when you describe. I'm going to show you another discontinuity then. This one is even more severe. Let's have a function start at 1 and it goes to here, which is 3, and then it jumps up here and it looks like this. And this guy here is at 5, and say this guy here is at 10, right? There's the whole picture. Would you agree this function has a problem at x equals 3? Won't the little fly get killed? In fact, doesn't the road stop and he smashes into a hole, right? He dies 2 different ways. Would it help if that dot was where the circle is? No, it'd still get killed, right? This has a discontinuity. This has a name. When you see this happen, you call it, it's quite a good name, a jump discontinuity. At x equals 3 in this case. So you can have a removable discontinuity, still a discontinuity. You can have a jump discontinuity. That's a very common feature.
I have a question.
Yes.
So in the previous one, the removable discontinuity, if that dot was there, would it be considered a jump discontinuity at that point, or would it be the okay.
That dot doesn't stop it. It's still called a removable discontinuity if that dot was there or if that dot was missing. It doesn't have any effect on the title. See how that dot is there? See if I move the dot to where the circle is now? It would still be a removable discontinuity. See if I made that a circle and that a circle, it would still be a jump discontinuity, I should say, right? So it's a jump discontinuity right now. If I move that dot to the below, it's still a jump. If I made both of them circle and didn't have a solid dot, it would still be a jump discontinuity. And if I went and made the dot up here, it would still be a jump discontinuity. Do you know that solid dot only tells you one thing? Doesn't it tell you the value of the function at 3 is 10? It doesn't have any effect on the discontinuity of the entire graph. Because there's still a problem at 3 no matter where that dot is, or even if you have a solid dot. Are we cool with that? Right, now there's one major one that we haven't talked about. And then there's a fourth situation where really, you do what you can. I'll try and explain it. Has anybody got an idea of something else bad that could happen? And you have met it in 141, graphs that have this feature.
Do you mean asymptotes or
I
infinity?
do. I do exactly that. Yeah. So can't you have curves that do this horrible thing? Don't vertical asymptotes, right? Now, let's see what's going to happen to my poor little fly. If he's in this car and traveling this road, doesn't he shoot off into space and dive through lack of oxygen? So my little analogy about the fly, do you see it kind of helps you when you're looking at a graph? Just travel from left to right and see what happens to the poor little fly. If it gets killed, you've got a jump, you've got a discontinuity, right? Might be a jump, might be a removable. In this case here, we'll call it a vertical discontinuity. And this last one has lots of different names. It could be an asymptote discontinuity. I've seen that term being used in a textbook, you know, vertical asymptote. Vertical discontinuity, I like, it kind of gives you an idea of what's going on, right? Infinite discontinuity, I've heard it called that, but not as often. We're just going to use vertical unless the textbook changes that for us. Are you comfortable with the three major types of things that can happen to a curve that makes it broken in some way, right? Discontinuous. Now, there is a fourth situation, which really, I don't even have a name for it because I don't think it's got a name. And it's kind of hard to draw, but we have seen one, a situation like this already. So let's put x equals 3 in. Can you remember the curve that went like this? And then it went, oh, yeah. Remember that one went up and down like nobody's business? And then maybe on this side, it went and did something really, you know, nothing too special. And nothing much happened at this side. Do you know one of those graphs where the function never actually gets anywhere? It goes closer and closer to 3 the more times it jumps up and down. That has a discontinuity. At x equals 3. So far, so good. I don't have a name for that. I mean, maybe you'll look up a video and you'll find out they have a name for it. I don't think it's got a name, but it's still got a problem, right? Yeah, that's very rare. You'll probably see one of those. Most of the ones you'll see will be removable, jump, or vertical, right? Those are the most common things that you'll see. You might see, you might not, but you might see one example of that happening. It's very rare. Any questions about the 4 kinds of discontinuities that a graph, a function can have? Feel good? Yes, Rachel.
I heard something once about ones that come to a point, but I can't remember if that had to do with discontinuity or not.
Ah, well, it might be what I'm about to do now.
Oh, okay.
So we'll find out. You can have a function, right, that's continuous or discontinuous at, say, a point, like at x equals 3, right? We've talked about that, right? But you can also have left continuous, right continuous. You know how we had left limits and right limits? Remember that? Left limits and right limits? You can have functions that are left continuous or right continuous. And do you know those little dots that you had in the end of pieces of these curves, right? See, like there's a little circle here, but there's a dot here. These pieces are very often called branches of a function. And the discontinuity at x equals 3, right? This would be called the right branch and this would be called the left branch. Now, in this one here, can you see that would be a branch? I would call that the left branch, and this one would be a branch, and this would be called the right branch. And where's my other guy? And here we go. At this discontinuity, wouldn't this side be called the right branch? And this one would be called left branch, and this one would be called the right branch. So when I say left branch and right branch, are you visualizing what I'm on about, right? So let's look at, what does a left and a right continuous look like? I'm only going to draw the piece of the curve that's important. Let's suppose at x equals 3, I have a guy that looks like this. Wouldn't we call that a jump discontinuity, right? This curve is left continuous at x equals 3, but it's not continuous on the right, I should say. It's not continuous at x equals 3. So what does left continuous and not being continuous? Do you notice that as you come in along this left branch, don't you reach the destination and that dot is at the end? You see that? The branch has a dot on it. If the left branch has a dot on it, it's left continuous. What would you expect then for this situation? Wouldn't this be right continuous? You see, the right branch has a dot in it. Now, can you imagine that you got a situation that looked like this? That shape isn't left continuous and it's not even right continuous. Do you see in both branches, there's a circle. The circle means the function isn't evaluated there, right? Does it help to put a dot somewhere? No. So this shape is left continuous at 3. This shape, this graph is right continuous at 3. And this is neither, right? It's not left and it's not right. So if you want to find out about left and right continuous, don't you just focus on this guy? Does the left branch have a dot at the end of it? Does the right branch have a dot at the end of it, right? A dot means the value of the function exists there. If that happens, you are left or right continuous. This would be left continuous and this would be right continuous.
So for the last one, would it be like does not exist or just?
Yeah, you could say it's not continuous, right? Discontinuous. Yeah, it doesn't have left or right, agreed? You could phrase that different ways. Are we comfortable with continuous and now this little extra left and right continuous? Let's go back to some of my early continuous graphs then. Okay, got all sorts of guys going on here. Right, let's take the removable discontinuity on this one. Right, would you agree this is not continuous at x equals 3, right? Discontinuous, if you want to call it that. It's called a removable discontinuity. Does this have left or right continuous at 3? No. In fact, won't every single one of these never have a left or right continuous because of the shape of them? Right. That a jump discontinuity, a removable discontinuity will never have a left or right continuous about it, right? Because don't they meet at the same point? They just have one a dot there. If I put a dot there, wouldn't the thing end up being continuous then? There would be a problem. Right, let's look at this jump discontinuity. At least the one I've written here. Is this one right continuous or left continuous or just doesn't have any? This shape here. Right continuous or left? It is one of them. Which is it?
Yep,
Right
it's right
continuous.
continuous.
It's right continuous. And the way you saw it was, see that little dot? If the right-hand branch is a dot, it's right continuous. If I rubbed that dot out, right, made it a nice circle, and I gave it to this guy, wouldn't it now be left continuous? Agreed? If I made both of these little circles, right, open circles, and I put the dot in the middle, wouldn't that make it nobody's continuous? Left or right? Nobody got the job. You might be thinking, so let me put this out your head, that you could put a dot here and a dot here, in which case the shape could be left continuous and also right continuous. But that is not allowed. And the reason that's not allowed is that these are functions. And way back when you did functions, for any given value of x, you're only allowed one answer, aren't you? And if you made that a solid dot, wouldn't that mean that there would be two answers at x equals 3? So that's never going to be a shape that you'll ever see, right? So when you do a removable discontinuity, couldn't you maybe get a left or a right continuous out of it? What do you think about vertical discontinuities? Can a vertical discontinuity have a left or a right continuous? What do you think? Okay, let's do the left branch. Or right. As you get closer to 3, does that have a value? No, doesn't it shoot off to infinity? No. That shape has never, that shape will never have a left or a right discontinuity. Because wouldn't they always be infinitely big? The closer you get, there is no limit. It has to have a number, right? There has to be a dot at the end. Would you agree that this left branch doesn't have a dot at the end? Because there is no end. Doesn't this just keep going on upwards forever? Are we good? Right. Let's put it to the practice. Let's go and look at some graphs in our homework, and let's see what kind of continuity or discontinuity they may have. So clicking on it, opening it up. Come on. There we go. Stop sharing. And I'm going to try and get as much mileage out of these questions as we can. Right. Would you agree that this poor graph get hit by a train? It is broke in lots of places, right? So let's focus on just names right now. So the names are going to be left continuous, not scrub that. The names are going to be removable discontinuity, jump discontinuity, or vertical discontinuity. Okay, that's the 3 answers you can give me. What is happening at x equals -4? I'm pointing at it with my mouse. What kind of discontinuity is happening there?
It's removable.
Removable. Okay, if I move to x equals -2, what kind of discontinuity is happening there? Starts with a J. What's happening there? Okay, jump discontinuity. What's happening at x equals 2?
It's the same.
Jump.
Another jump. It's hard to give a name to 4 because in a way, isn't it a bit of a jump discontinuity? But I'm assuming that that goes vertically downwards, right? And so it's got a little bit of vertical and it's got a little bit of jump. So that doesn't have a name. But remember, the zigzag one doesn't have a name either. So wouldn't we just say that it was discontinuous at x equals 4 and call it good? Now, let's go back to this shape again. At x equals -2, right, where my mouse is pointing up and down, x equals -2. Left or right continuous? What's it got? At x equals -2, what does that shape have? Left continuous or right continuous? Because it has one of them.
Left
Would it
continuous.
be
Left.
left?
It'd be left. Try and ignore all the other stuff. It's kind of hard when there's a lot going on. But would you agree the left-hand branch ends in a dot and the right-hand branch ends in a circle? And that means if the left branch has got the dot, it's left continuous. If the right-hand side has got the dot, it's right continuous. Okay, let's move over to x equals 2, this one here. Left continuous or right continuous this time?
Right continuous?
Agreed. That weird one that has no name. Left continuous or right continuous?
Right, continue.
Right. Would you agree the right branch? Would you shushed? Where are you? That's probably the wind blowing again. My dogs get excited for it. Are we good with that one? Call it pretty much a thought of everything. Oh, well, maybe not. What about this function at x equals 0? What's going on here? The function is, insert missing word. The function is,
Is it continuous?
it's continuous at x equals 0. In fact, isn't it continuous at x equals 1? It's continuous at x equals 5 and 6. Have you noticed when a function's continuous, nothing's happening. It's really just passing through like it normally does. Okay, another one. What is happening? Oh no, let's do it a different way. Tell me the x coordinate of a vertical discontinuity.
-1.
Right, so there's a vertical discontinuity, x equals -1. Give me the x coordinate of a removable discontinuity.
-2.
Agreed. What is happening at x equals 1? What name would we give to that discontinuity at x equals 1?
Jump.
I jump discontinuity. For this function, at x equals 1, does it have, is it left continuous, right continuous, or it just doesn't have anything? What's happening at x equals 1? Left, right, or it doesn't have any?
Doesn't have any.
Agreed. At x equals 0, left or right, or it doesn't have any kind of continuity? At x equals 0.
Left.
Okay, left. Are we getting comfortable now about left and right? Once you see a few more, hopefully, if you haven't got it by now, you'll get it. Here's a trick question, but it does have an answer. Do you know at x equals 3, there's a little dot there? And then the function just stops, right? There's nothing else after it. At x equals 3, this function does have left or right continuous. What would it be at x equals 3? Left continuous or right continuous? It does have one of them. Can't hear you, Rachel. Yes. Would you agree that this is coming in from the left? I know there isn't another side, but you can do that. What's happening over at x equals -3? Is that left or right continuous then?
It's from the right.
So it's right continuous.
Mhm.
So what, to recap and to finish for today, what we have looked at is we did a quick homework on the formal definition of limits, and I'm not going to say any more about that. And we did a lot on functions being continuous, right, and discontinuous. And we looked at the major types of discontinuity. There's a removable discontinuity, a jump discontinuity, a vertical discontinuity, or just a discontinuity that has no shape because it's weird, right? And then we talked about left continuous and right continuous, or it just doesn't have anything, right? And that's kind of where we finished.